No problem.
So
Please.
yeah, thank you. Fine. So am I audible that side?
Yes,
And you can
clear,
see
very
my
clear.
screen?
Yes, visible.
Thank you. Thank you. So good morning, everyone. As Subbu told, I'm Dr. Afzaal Ahmed, working in Department of Mechanical Engineering as assistant professor from past 3.5 years. And for today's talk, which is on dimensional and form characterization of metal additive manufactured components, I'll be taking this particular topic from the point of view of the theme of the workshop, which is additive manufacturing from lab scale to the field scale. So my focus will be on what are the efforts in the lab scale to make this particular topic of additive manufacturing bigger at the field scale. So this is the outline of my presentation. I'll start with introduction, move on to explain what is lab scale to field scale. Then I'll talk about the need and demand. Where is the need and how is the demand for these components? So I'll take a specific example of a field scale case study, and then we'll say how the need is arising and where is the demand coming from. Then we'll talk about the challenges. We'll talk about the challenges in metal additive manufacturing. What are the post-processing steps needed, okay, before the item can be consumed in the field scale? Then certain surface modification applications, trends in improving dimensional accuracies and form accuracies, followed with conclusion and references. Yeah, so all right, we'll start with the introduction, which is additive manufacturing from lab scale to the field scale. So let us explain what do we mean by lab scale to field scale. So if you see here, lab scale or field scale includes all these things. Okay, so I've highlighted few industries, but there is much wider scope of additive manufacturing in other parts of other sectors of the industries as well. But I've highlighted something on aerospace, then automobile, then biomedical application. And where do we use such components in these industries? We use it for aircraft brackets, jet engines, prototyping and repair of automotive parts. And in biomedical industry, we use in fabricating hip implants, knee implants, dental implants, and much more. Okay, so these are the requirements at the industry level. But if you see what are we doing at the lab scale, here is what we are doing on the lab scale. So if you see, we are doing 3D printing. That means additive manufacturing, be it polymer based, be it metal based, but we are doing 3D skill at prototype level. Okay, we are not fabricating whatever components like jet engines or aircraft brackets or let's say hip implants and those things at that level. We are doing printing at lab scale level or at prototype level, okay, by investigating various aspects like the topography, the CAD modeling, the slicing patterns, and then various process parameters. So we are understanding the behavior of the prototype with respect to all these parameters. Now the next step is the post-processing, which is inevitable basically. Why? Because we'll discuss in further slides that what happens once the product comes out from the printing chamber. So what are the various defects? But we have to mitigate those defects. How can you do that? You have to go for certain post-polishing steps like heat treatment, polishing, grinding. There are many more processes which we'll discuss in details in the coming slides. And the final step is the testing and inspection. So testing and inspection is another important step which can be performed based on non-destructive testing or various ways of measuring the dimensions using CMM, coordinate measuring machine, measuring the surface quality, the integrity, as well as you are finding out the various parameters which suits the field scale requirement. Now, this field scale, based on all these investigations at lab scale, so whatever we just discussed on lab scale here, based on all these investigations on lab scale, we propose a set of methodology, or I would say a set of parameters, as well as inspection techniques, as well as post-processing methods to suit a particular field scale industry. Okay, so let's say if we are talking about aerospace industry, so the size of the components are very big. Okay, so certain things which we do at lab scale may not be applicable on such a big component. So you have to develop the testing facilities for such components. Let's say a jet engine component. Okay, such a big component, or a fuselage, a part of a fuselage of an airliner. Similarly, for let's say implant industry, you have to develop a setup where you have biocompatibility ensured on the lab scale. Okay, similarly on the field scale also, you have to bring out the parameters from the lab scale which make sure that the output of the particular implant manufacturing should be compatible with the human body. So these are the challenges. Okay, but we are in a continuous process of learning from the challenges from the field scale. So if you see here, this particular field scale industries gives us a continuous feedback. Okay, gives us a continuous feedback like this is wrong, this can be improved, this can be enhanced. If we do this way, this can give us better output, something like that. So this feedback is continuously coming back to the lab scale. Okay, so we can see that different industries will come up with different feedback. Okay, a biomedical industry will come up with a different feedback, aerospace industry will come up with a different feedback. But on the lab scale, we have to take those suggestions and feedback from them, and again start working on removing those defects, or removing those anomalies, or removing those problems and issues faced at the field scale. So if you see, whatever we are doing at lab scale is very much applicable on field scale, but not at the same scale. So what we have to do is we have to do the testing at a smaller scale, but those testing results are very much applicable on a bigger scale or industries like aerospace, biomedical, and automotive. So this is a brief overview why both are important. Okay, field scale definitely goes for implementation. Okay, so this goes for your implementation on let's say a airliner or an automotive vehicle, or a body inside a body of a human being. So here we are implementing whatever we are doing here on the lab scale. Okay, so instead of putting an arrow like this, we could better say this is something like this. Correct? So they both go hand in hand. So with this brief introduction, let us move to the next slide, where I'll take a specific case study. Okay, so these industries for additive manufacturing is very vast. You cannot cover everything in one and a half hour time. So I've taken a specific example of biomedical implants industry. Okay, and if you classify these biomedical implants, they are basically classified or broadly classified into three. The first one is orthobiologics. The second one is reconstructive joint replacement. Third one, which is very important, is trauma and craniomaxillofacial implants. So these craniomaxillofacial implants basically means is the implants needed after an accident. Okay, because these are trauma-based implants, and craniomaxillofacial is basically related to your face. Which includes your skull, okay, the jaw of the patient, okay, and the frontal forehead. Okay, so these are the major implants related to craniomaxillofacial. Orthobiologics, we will not go into details. These are polymer-based. Implants, and we are not talking about polymer in this talk. I'm basically covering metal additive manufacturing implants, and these are used for healing the patients. Like you need ligaments. you need ligaments to support the bone. Okay, so these are made usually from polymers. Now, other important category of biomedical implants is joint implants. Okay, reconstructive joint implants, which is hip implant, knee implant, and an ankle implant, all this. And these are also needed at different age groups level as well. Okay, so sometimes the injury happens because of an accident, but in most of the cases, these kinds of implants will be used in higher age groups, like 50 plus, 60 plus people, where normal wear and tear of knee and hip takes place. Now, this is kind of the overall broad overview of a field. Okay, so because we are discussing about field scale, so this is a broad overview of a field which is biomedical industry for implants manufacturing, specific to implants manufacturing. Now, let me give you an example here of a knee implant. If you see here, this particular part is femoral component. Okay, the bottom component. So we are talking about knee implant only. Okay, so let us be specific in implant industry also. So the another one is the tibial implant. Okay, so tibial insert. The third one is tibial tray. So this tibial tray is the bottom part. Tibial insert is again made of polymer, which we may not focus now. And femoral component is again metallic. Okay, so this is the frontal view of a complete knee replacement implants. This is the view from the back. So this femoral component looks like this from the back. There are different attachments and fixtures to join it to your bone. Then you have something like this part which goes inside your tibial bone, and there is something in between so that this metallic surface does not rub against each other, which is known as tibial insert, which is again a soft polymer based material. And when these implants are mounted on the bone, it looks like this. So this is the human bone, and now after removing certain parts of from the top of these bones, these implants are mounted. So this is how the implant looks like after replacement. Now, what is the present way of doing this implant fabrication, or what is the present way of manufacturing these implants? Now, if you see, we start with a CAD model. Okay, so basically you get the CAD model from the MRI scan of the patient. Okay, so the doctor takes an MRI of the whole bone, and they send you the MRI scan data. Now, from that data, you create the model of femur bone and the tibial bone. Okay, now, and these are highly patient specific. Okay, so all these CAD models are patient specific. Okay, so if I am preparing a particular implant for a particular patient, that may not be suitable for any other patient in the world, because all of us are different different by nature. Okay, so we are talking about patient specific implants. So when you get the MRI data from the doctor, you have to prepare a CAD model out of it. Then printing of wax models can be done. So the femur parts or the tibial parts, printing is done on very sophisticated wax. Okay, and these wax will act as a pattern. Okay, for mold fabrication. So you start with the wax pattern. Okay, then you prepare a mold out of it. Now, the material involved in fabrication implants are basically cobalt, chromium, Ti-64 alloys, stainless steel alloys, and it again depends on how much the patient is willing to pay. Okay, if he has money to pay for a titanium implant, he can go ahead with titanium. On the other hand, the cheaper version will be a stainless steel alloy. So then that particular alloy is melted and poured into the mold. Casting and solidification will happen. Once that is done, machining can be done on the rough surface which is produced from casting. Then multi-stage grinding process. Okay, multi-stage grinding process has to be performed to polish the implant. As you can see, it is very shiny. Okay, so these surfaces are very shiny, and you have to wear, because these are sliding kind of joints. A knee joint is a sliding joint. Okay, if you have lot of roughness on the surface, that may not work. Okay, that may not work for long, and you have to see the long lasting capability of these implants also, the longevity of these implants. It should last long, so that the patient does not feel any pain in the knee. So this step is ensured with grinding and polishing, and finally the inspection based on automated CMMs, and then packaging, boxing, and everything is done and sent to the hospital for the surgery. So as you can see, there are multiple steps involved here, and every step has a cost involved to it. Okay, so we'll talk about basic cost for fabricating such an implant. So if you see what government has done recently, by the way, this NPPA, you might be wondering what is this. This is National Pharmaceutical Pricing Agency. Okay, so this is National Pharmaceutical Pricing Agency, which decides the ceiling price of each implant. So what Indian government has done recently means like in 5-6 years, that they have fixed the ceiling price of these implants, because these are basically associated with senior citizens, knee implant. So I'm giving you the chart of knee implant only. Okay, so if you can see here, based on the material, like femoral component, if it is made of titanium alloy, it costs around 40,000 rupees, including GST. So this is the ceiling price. So whoever sells this made of titanium, okay, they cannot sell it above 4677. So this is the price set by the government. Okay, so whoever is fabricating these implants, they have to stick to this cost. Okay, so you can see there is an upper band to the cost for a femoral component. Similarly, with varying materials, if you can see, femoral component with oxidized zirconium is slightly cheaper. High flex is again cheaper. Cobalt is 25,000 rupees. Then you have titanium alloy for tibial components. So you can see all these things, all these prices listed here. Now, this is for the first time knee replacement. So if you see, the prices are much cheaper, 40,000, 25,000 for a tibial component made of titanium alloy. Then you have a patella also. Patella is basically the kneecap, which you can feel with your hands on top of your knee. That's the kneecap, patella. So that is around 4,000, 5,000 rupees for fabrication. Now, if you include everything, it will roughly cost you less than 1 lakh rupees. Okay, and to prepare something or to fabricate something in less than 1 lakh rupees is a very challenging task. Okay, so most of these implant fabrication industries like Stryker, if you talk about Bosch, all these industries are struggling to bring down the cost. Okay, now this is, I'm talking about from the point of view of replacing the implant or replacing a particular part of the knee, be it a femoral component or a tibial component or just a patella. But let's say if someone goes for the repair of the knee, repair in the sense he has already done a surgery, and after 5-10 years or 20 years, again some part started wearing off, and then he started feeling pain, and now he has to replace or do some repair to the implant in their knee. So the cost is totally different. You see, the cost is so high. If you see femoral component, any material, it is fixed to 65. Tibial component, it is fixed to 32. Patella, it is fixed to 4,000. And again, this will easily cross 1 lakh rupees just for repair. Okay, so this repair cost is much higher compared to the initial cost, and these costs are fixed by the government. Now the implant manufacturing industry cannot charge you anything. Okay, and this data, by the way, is taken from Max Healthcare website. Okay, Max Healthcare website, which is one of the leading chain of hospitals in India. Okay. Yeah, so now from additive manufacturing point of view, is it possible for us to fabricate these implants or these components of knee? When I say implant, it doesn't mean only about knee implant. I'm talking about the overall industry. And since I've taken the case study of biomedical implants, it doesn't just stick to the biomedical industry. I'm talking in overall sense that how does an aerospace industry or an automotive industry, all these industries uh, can cut down the cost for fabricating a component. Okay, so if you see the previous step, here basically the fabrication process involves removing lot of materials. Okay, so this is something which involves removal of material. Okay, but in case of additive manufacturing, we have near net shape. Okay, we are producing a component which is very near to the actual component. Okay, so the amount of material wasted is very less. And if you see the cost of this particular implant here, made of titanium alloy, a femoral component of a knee, it is around 40 odd thousand rupees. And most of the charges out of this 40,000 goes into this material only, titanium alloy. So how much, like if you're spending a 40,000 rupees, majority of these 40,000 rupees goes to the material. Okay, why? Because here in this case, when you are fabricating using casting and solidification, then machining, grinding, all this process, you are wasting a lot of money. Okay, so when you are wasting this money, which wasting a lot of material as well, which leads to wastage of money. Now, if we can cut down the cost by making near net shapes using additive manufacturing, the material cost has drastically gone down. You don't need that much of material at all. And that material, whatever you use, which are powders basically, can be reused again in the next cycles of printing. So here we can cut down the cost, and easily we can bring down these costs to around 50 to 60,000 rupees using additive manufacturing. But still, there are a lot of challenges to encounter. There are a lot of challenges to overcome. So we'll talk about those things in some of the coming slides. Now, this is a very important slide. So since I talked about the price here, the replacement price here, but everything depends on the need. Where is the need coming from and where is the demand? So the demand comes from this particular slide. If you see, in the world, 1.3 million people lose their lives every year because of road accidents. Okay, and this is the data taken from road accidents report by WHO. Okay, so 1.3 million people in the world every year lose their life because of road accidents. India ranks first in the number of deaths linked to road accidents in all 199 countries. So India is the first in number of road accidents among all 199 countries, followed by China and US. And if I specifically talk about a particular year, the latest report which was available on Ministry of Road Transport and Highways, the latest report was from 2019. Every year this ministry publishes the report on their website. The latest report which was available was from 2019. A total of 4,49,000 road accidents have taken place, out of which 1,51,113 people lost their lives and 4,51,000 odd people has suffered grievous injuries. Okay, so here's the need coming from. When you talk about a biomedical industry, where is the need and where is the demand? So the demand is coming from some unfortunate accidents which are happening every day on our roads. And the data also suggests the same, that in just 2019, almost 1.5 lakhs people have lost their lives and 4.5 lakhs have suffered grievous injuries. And as you can see here in the graph, I hope I am audible to the audience.
Yes, Afzaal. Yes, please.
Thank you, Subbu. So if you can see here from the map, the Indian map, so the peach color, this is the peach color. I hope you can see the markings on the slide as well, Subbu.
Yes.
Yeah, thank you, thank you. So this peach color represents the number of road accidents above 30,000. About 30,000. So this is the highest, and the lowest is this green color, which is below 5,000. Okay. So you see this green color is very rare in the Indian map. You can see Goa or some northeastern states, you can only see where the number of accidents happening every year is less than 5,000. But the majority chunk, which is above 30,000, you can see it here, which are the states like Madhya Pradesh and then UP, Bihar, all these states, including Kerala, where we are sitting now. So this is very unfortunate to see, and this rise in road accidents also is also very difficult to stop on Indian roads, because every day the number of vehicles increasing on the road, people are going out and buying more and more vehicles, so it is kind of inevitable to stop the road accidents. And in some sense, we don't take care of the safety as well. So this is the broader picture of the need and demand of biomedical implants in India, and which is not very pleasant to see. Now, then we have plotted some more results from the report, and which is a bit shocking to see. So they have tabulated all these results in the report, but we have plotted it for the easy understanding of everyone. So if you see number of grievous injuries, okay, number of grievous injuries happening every year. Oh, this data is only related to 2019. Okay, but if you see, it is increasing from 2015 to 2019. So this is grievous injuries. Grievous means serious trauma implants are needed, trauma or craniomaxillofacial implants. So for such cases, you have to deal with very sophisticated and patient-specific implants, because whenever an accident happened and which leads to a grievous injury, you don't know which part of the body gets affected. Okay, sometimes the head gets affected, sometimes the frontal part of the body gets affected, sometimes the legs and hands gets affected, and which leads to a very customized or personalized demand of the implant. Okay, and again, you can see the unfortunate rise in increase of these grievous injuries over the years. Now here on the other graph, if you see, this is highly dependent on the age group as well. Okay, so this data was again available in a tabular form, but tables we cannot understand in a better way, so we plotted it. And what I found here is, you see, in the age group of 18 to 25 and 25 to 35, okay, the red one shows the male and blue one shows the female female candidates who are undergoing or who are meeting these accidents. Okay, so in the age of 25 to 35 and 18 to 25, there is high chance of people meeting an accident on the road. Okay, and which is very obvious, because this age belongs to young age of the students, where the student goes to their tuition centers or coachings, or people go for their jobs, so they are mostly on road. Okay, these people, this age group people are mostly on road, be it female or be it male. So by this particular graph, what I wanted to show here is the age-wise requirement and gender-wise requirement of these implants are also varying. So you see the diversity of the demand in implant industry. Okay, the male and female, two bodies are not same, be it male or be it female, first thing. Secondly, the age group wise, if a 10-year-old met with an accident, the type of implant needed is much smaller in size compared to a person who is 40 years or 50 years old. Okay, so the demand is very personalized, very customized, and very much patient specific. Okay, so this particular slide shows that. And if you see above 45 to 60 and 60 and above, from this particular slide, in this category, people don't go that much on road, but there are some accidents reported in this category also, age group category. But mostly in this particular age, the demand of implants is basically from reconstructive joint implants, because it is mainly because of wear and tear. And this data is again taken from the Ministry of Road, Highways and Transport. And this particular data is from 2019. After that, there was no report available on the website. So the crux of this slide is, first thing, the demand is increasing, okay, which is not very pleasant to see, but still we have to cater to this demand because these people need attention. Okay, these are all traumatic accidents and these need attention. So the demand is increasing, and the demand is not very linear. Okay, or rather I would say the demand is very much patient specific and gender specific as well as age specific. Okay, so you see the complexity for the implant or bioimplant manufacturing industry. So this is a broader overview of things panning out in Indian context. Okay, so let's move to the next slide, which is on types of bone implant. We have briefly discussed this. So you can see this is a kind of craniomaxillofacial implant. Okay, so you see here, this particular thing has been replaced, which is a part of a skull. Okay, then you have humeral fracture. This is kind of extremity implant. Then you have femoral implant, which we have already discussed, which related to knee implants, and then this ankle implant. So there are different varieties, and you don't know when an accident happens on road, which part of the body will get affected, and you have to be ready because the doctors will send you the MRI scan, and then you have at like 3 to 4 days time to come up with this patient specific implant. Okay, fine. So what are the materials, implant material properties you need? Basically, the biocompatibility is very important, corrosion resistance, because the whole thing has to be inside the body, so that it should not be corrosive. The strength is very, very important because it should match with the strength of the bone, which was there before. And then there are different varieties of materials available. Polymer, which is basically used for organobiologics, which we are not discussing in this particular presentation, but this itself is a big industry, and this calls for a separate presentation, polymer based organobiologics implant. Then we are talking about stainless steel, titanium alloy, cobalt chromium. These are the major materials used for bioimplant fabrication because they are biocompatible, good in strength, and high resistance to corrosion. Okay, so now if you see here, the conventional bioimplants, what are the limitations? So we, as I said before, we use it by casting, and in some cases we use powder metallurgy as well for fabricating such implants. But what are the problems associated with this fabrication process? So basically economic losses, because there are multiple steps involved, right? From making the wax pattern to finishing using multi-stage grinding, then inspection, and then right to the last step, which is boxing. Okay, so the process has a long chain of steps to follow, and then the cycle time will ultimately increase because of that. Post treatment is again very subjective, but again depends on the type of implant which you are making. And if you talk about powder metallurgy, then these powders are basically, you need high compaction pressure. If the implant is too big, how will you make a bigger implant? If a implant belongs to a part of your skull, then making such a die and mold becomes very difficult. So these challenges are always there. Now, how metal additive manufacturing plays an important role here? Okay, so again, I've prepared this particular slide in relation with biomedical implants, but it is very much applicable to any industry you pick from the present scenario. Okay, so you see here, in case of when we talk about benefits of metal additive manufacturing, you see the design freedom. This is very much needed in case of any biomedical implant fabrication industry. Why? Because as I told you, the implants are age specific, then gender specific, and then again it is specific to the injury as well. Okay, so you need a design freedom which metal additive manufacturing provides you. Then mass customization, definitely again mass customization, because not every accident is same. Okay, not every accident is same. And let's say a cortical bone fracture has happened. Now that cortical bone fracture can happen in 100 different ways. Okay, so one person has met an accident with a cortical bone fracture from the middle, let's say, with a 45-degree inclination, but another person has faced just the chipping of cortical bone where you need a repair. Okay, so these are very customizable implants. Okay, so you have, the demand is very customizable, so you have to be very much flexible in making such kind of implants. Then again in batch production, definitely, because AM provides you components in batches only. You cannot do a mass production in additive manufacturing. So, and the demand here in implant industry is again batch production only. You need one or two specific implants, and then you have to change the whole settings and do it for a separate person separately. And again, very important point is minimum scrap, which I have discussed and touched upon initially very briefly on this, that this defines the cost, because all these biocompatible materials which we have discussed, like cobalt, chromium, titanium, aluminum, whatever you discussed, are highly expensive. And if you lose this material in multiple steps of casting, machining, grinding, polishing, then you are adding everything to the cost of the final product. Okay, so this is a very much important step in case of very much important advantage of a metal additive manufacturing process. Basically, you take a 3D design data and then you fabricate using layer by layer. So I'm not going into that because from last 2 days, people have covered much on that. And here you can see a hip implant, which is fabricated using additive manufacturing. So this is a hip implant, which is fabricated. And you can see here, this implant is with varying density. Okay, because our bone is not a solid bone. It is made of pores inside. Okay, and when you do a casting, you cannot involve these pores inside the casting, because it will be a solid thing. Okay, which is not possible in case of casting. But here in case of additive manufacturing, we can add that feature as well, where the ultimate implant will be very lightweighted, first thing, and secondly, it will match 90 to 95% the properties of the bone. Okay, so this is again an advantage of AM. Okay, metal AM. Okay, so moving on to the challenges. Now, not everything is greener in metal additive manufacturing as well. You have to overcome some of the challenges, which are basically related to stair-stepping effect, balling defects, porosities, voids, cracks, and all these things. Because this is a complex process, we are dealing with metals, and metals behave differently at different temperatures. So you have to take care of all these things. And if you don't take care of these things properly, what happens? These are the defects which are shown on the right-hand side. Another important defect is when you do curve approximation, then you come up with stair-stepping defect, and porosities are basically because of lack of melting or lack of fusion sometimes. Okay, so these are the major defects. I'm not going into the details, but as you can see from the picture, these are the major defects in any metal additive manufacturing process. So again, speaking from the point of view of a knee implant, okay, as I said initially, the roughness plays a vital role for the life of the implant. If the roughness is not as per the requirement, then the component may not survive long. Okay, so we have to work on the overall surface integrity of the final component as well. Now, people have attempted many methods. Okay, so I've listed down some of the methods here, which are very much used in the industry. I'll just take a water break for 20 seconds. Subbu,
Please,
is
Afzaal,
it fine?
please, Afzaal,
Yeah,
please.
yeah. I'll just take and come back. Okay, so yeah. So let's talk about the post-processing methods, what people have been trying over the years. And some of the major methods are laser polishing, abrasive finishing, conventional machining, chemical polishing. And as you can see, all of these methods can give you a finish value of less than 1 micrometer. Okay, so but there are challenges associated with each of these processes as well. If you see here, in case of laser, okay, you have, this is basically a thermal process. Okay, thermal process with limited spot size. I think I've kept a slide on this, so let us go to that. Yeah, so let us talk about the individual limitations of these processes. So if you talk about laser polishing, very small spot size, okay, which let's say if you have to do a bigger job or a bigger workpiece, it will take ages to complete that job. Okay, so the spot size is very small, so polishing using that may not be feasible. Larger areas, and since, as you all know, laser involves a thermal energy, or laser is basically a thermal source. It consumes a lot of energy, so the final product may not be that economical. Chemical polishing, speaking from the point of view of, again, medical industry or implant industry, this is not feasible because these chemicals may react with the body parts of the patient and then leads to many more complications. So this is ruled out specifically for a biomedical implant industry. But what are the problems with this associated with this particular method is loss of dimensional accuracy, because you don't have any control over it. Okay, so this is basically when you dip a sample inside a chemical, you don't know what amount of chemical will react with what surface and how much material will get dissolved. Okay, there are sophisticated masks available these days, but that again takes a lot of time to prepare such masks. So this is one thing, and the second important thing is, and it is not environmentally friendly, and it involves high risk of toxicity. Third one is abrasive polishing, very difficult to process internal channels or components or holes, because these abrasives will go and sit inside. Okay, or if you do some internal channels, they will get stick to the internal channel, causing further roughness on the surface. And high cost of abrasive media, again, these are SiC, or for finer materials finish, you use CBN or diamond powders. Okay, diamond abrasives. So these are again expensive. And mechanical, again, mechanical means like you do machining, 5-axis machining or milling on the surface to get the final shape. But again, this is subtractive. You lose material first thing. Secondly, you have if you have very complicated features to machine, the tool may not be able to reach at that point, and then you cannot finish certain regions on the job. And when you specifically talk about implant, this is very challenging for mechanical processes to reach those smaller areas. So if you see, all these existing methods which have been there from at least 1 decade have associated with all these challenges. So what is the better way to go ahead, and how can we counter all these challenges in some way? So we started research in exploring wire electrical discharge method. Okay, EDM, we all know what is EDM. It is basically sequence of sparks to remove material from the surface. you have the job dipped into a dielectric medium, and then you apply a potential across the electrode, and based on the CAD drawing or the CAD model, or basically the CAD program, you get the final surface on the job. So we thought this is also a kind of machining process. And if you can see here in the previous slide, people have been using mechanical processes like milling or kind of drilling or some other methods to process these implants. Okay, so why can't we use a non-conventional method where the things are slightly easier to handle, okay, compared to other processes, and the reach of this process is much higher compared to the other process, okay, which I'll explain in some of the coming slides. And again, if you see, people may argue that, okay, EDM is basically a thermal process. Okay, so if you use a thermal process after additive manufacturing for polishing the component, you may impart more tensile residual stresses. But if you see here, laser, which is the major post-processing process in the industry now, is also a thermal-based process. Okay, and the energy involved for polishing using a laser process is much higher. The energy density is much higher compared to wire EDM. So we started with this, and then what we planned here is to modify slightly the process for our requirement. That is, instead of using a random energy, we'll use a very low discharge energy for polishing the surface. And we start with very low polishing energy. Here you can see the schematic. This is the rough AM surface. Okay, this is the rough AM surface. Here's the wire electrode. This is a 2D schematic. So the whole process happens in 3D. I'm just showing you the 2D schematic of the process, and this wire is continuously moving in this direction. And we are not cutting here. We are just passing the wire across the surface by maintaining a specific gap between the workpiece and the wire. And we are just removing these unnecessary peaks on the surface. Okay, so there is no cutting happening. Cutting means if I cut through like this. So there is no cutting happening. Only the frontal part of the wire is involved in polishing. And the important thing here is we use very low discharge energy. Okay, so the amount of thermal residual stresses, okay, imparted to the final job is much lesser compared to a laser polished specimen. Okay, and these are the basic methodology, which I'm not explaining. You can see it here, the steps involved to set up the whole process for wire electrical discharge polishing. Now, if you see here, these are the experiments done in our lab at IIT Palakkad. If you see, the metal sample is printed, and if you see, these are the defects available or is present on the surface. These are partially melted particles, balling defects, all these defects which shows huge irregularity on the surface of a finished or a printed component. On the other slide, you can see white spaces. Okay, you can see small pits. Okay, spherical porosities on the surface. So these are also present, and we have to encounter both these. And when we perform low discharge wire electrical discharge polishing, you can see here the finished surface obtained after that. Okay, so all these irregularities, the balling defects, the porosities, the cracks can be removed because these are all superficial surface defects. Okay, these are only available on the surface. And if you talk about these porosities and all, these are also available. These are also present on the surface, not to much higher depth. Okay, so this can be removed with a single pass of polishing. Okay, and if you feel, you can take the same sample to under the microscope and see whether the whole things or all the impurities or the defects or anomalies were removed or not. You can go for another pass for wire EDM polishing. And then we have devised a strategy for number of passes also, which I'll be discussing in some of the slides later. So we saw a huge improvement in the roughness. So initial roughness of these samples, as you can see, in all the parameters, SA, SQ, and SZ, okay, was initially around 10 microns. 9.36 was the average roughness, and then we have reduced it to a very low value after wire electrical discharge polishing. So here you can see we have achieved approximately 90% improvement in the surface roughness. So here the as-built surface roughness was 9.36, and we have gone much below 1 micrometer after doing low discharge spark assisted machining or polishing. Yeah, these are the topographical representations of the surface before and after. So this is as received. As received means the component which just came out from the printing chamber, and this is after WEDP. Now, there are different process parameters, as you all know, in case of EDM. And as you tweak any process parameters like voltage or current or T on and T off, the direct impact is on the discharge energy. Okay, so we had a very limited window to check the feasibility of these process parameters. Okay, because as you go beyond a certain limit, the discharge energy will increase, and all the problems related to a thermal process may appear on the final component. So we did not want that to happen. So we moved in a very narrow window, and we tried to investigate the effect of current. So as you can see in the first slide, sorry, not current. This is regarding the T on time, 10 microseconds, 5 microseconds, and 15 microseconds. And if you go beyond this, then you ideally go into cutting regime, and which we don't want to enter there. So if you see here, ABC, you have you can see an increasing trend in roughness. That means if you increase the T on, the roughness will increase, which ultimately means that when you increase T on, the discharge energy will increase. Once the discharge energy will increase, then the spark happening will have much energy. That means it will create a bigger crater on the surface, okay, and which leads to higher roughness. So, and definitely this does not impact the machining time or the polishing time that much. When you move from 5 microseconds to 10 microseconds to 15 microseconds, there is hardly or barely any difference. Okay, so it is always recommended to go for lower settings of T on, current, and all these things. So ultimately, the energy, the discharge energy which we are talking about for polishing should be very, very low. Now, these experiments we did on SS316L, okay, stainless steel, which is again a biocompatible material, but we wanted to try the same concept on titanium aluminum alloy as well. Okay, so let's say this particular thing works for that, but it may not work for this. So we printed some of the samples using titanium aluminum alloy, and then we repeated the whole step on this particular alloy, and we found the same results in case of titanium aluminum alloy as well. So that means this process is compatible with almost every biocompatible material. Okay, and as we all know that EDM basically needs electrically conductive material. Okay, so we were sure that it will work on titanium, but the problem, the challenge which we were thinking in our mind, or the thought process was like whether we get the same range of improvement or not. That was our thought process, because every material behaves differently, and that melting point of the material is different. So all these things, and then microstructure plays a very important role. So those things, so we tried that, and we found that it is also giving us similar levels of surface integrity. Okay, so this particular graph shows the EDS spectrum before and after polishing, and as you can see, there is slight migration of materials, migration of wire material, okay, from the wire to the job, and which is unwanted. We don't want this, because let's say if we are using this particular process for a biomedical application, we don't want these impurities to happen on the surface or to adhere on the surface of the component. So we are still working on it, how to reduce it, but this is very minimal, as you can see. So actually we have used as brass coated zinc. Oh, sorry, zinc coated brass wire. And these two materials, copper and zinc, is coming from there only. So we are trying to go into ultra fine regime now of discharge energy to see whether we can minimize this further or eliminate this further in the process. Now, in the initial slides, we have discussed that all these implants must have a level of strength. Okay, strength in the sense like our bones are made up of some material. Okay, that material has some strength. Okay, if I hit my hand on the table, nothing happens to my bone. Okay, but if I hit it with a hammer on my hand, then there is a chance that my bone may crack or some kind of failure may happen. Okay, so that we don't want in case of implant also. So this has to be under loading conditions all the time. Okay, so we have to find out the strength as well. And then after wire electrical discharge polishing, we did the hardness testing, and we found that the hardness of the top surface has improved. So as you can see here, this is the base or bulk material hardness, and on this side up to 200, let's say 70 or 60, 250 microns, the hardness has improved in this particular range, which means that if this particular implant, which is polished using wire EDP, has to go for a kind of wear application, okay, this will survive there because of the improved hardness on the surface. Now we tried some tribological testings as well on the surface, and then as you can see, after polishing, we have found compared to other processes, the coefficient of friction is minimum 0.35 compared to the processes like as received SLM, then SLM with laser polished, SLM with maybe some other process. But here in our case with WEDP, we have reported, these results are already published, we have reported that 0.35 is the minimum as COF, coefficient of friction, which we get. So that means the implant, okay, which is polished, or the component which is polished, has much better performance in wear as well. And here you can see, ideally the material is not the same. Here we are talking about SS316, and here it is Inconel, which is as received, but still it is on the higher side. So if we have, I think I have not presented the data on as received SS316 here, but it is there with us. But it is again much better compared to all the existing polishing methods. Now this is the wear track morphology. So if you can see here, these tracks are very narrow in size. Okay, that means the surface after polishing is very much resistant to the wear to happen on the surface. So these are very narrow tracks. Okay, and if you see here, with increasing time, wear testing time, the track width or the wear height, okay, the depth at which these wear tracks will take place on the surface is barely below like 60 to 80 microns. Okay, depends on the wear testing. Okay, the loading conditions have been given here. Okay, so if you increase time, you see the height varying in this fashion. Okay, now let us talk about dimensions. So this is again a major challenge. So where these dimensional inaccuracies are coming from? Basically, this is additive manufacturing. Metal additive manufacturing is a thermal process, okay, where melting and solidification is involved. Wherever there is solidification involved, you can always think of something called shrinkage. Okay, so when the final component comes into picture, that will be a shrinked version of the CAD model, first thing. Secondly, this we are doing layer by layer. So there is something called layer shrinkage also. Okay, so layer shrinkage will also play an important role in the final dimension of the component, and other anomalies are like layer warping. Okay, so when you print one layer, in the meantime, that layer is exposed to the environment in the chamber, exposed to the argon gas or nitrogen gas environment in the chamber. So that layer starts solidification. And in the meantime, the recoater blade will do the recoating on the surface. So in that particular period, the temperature gradient in the atmosphere, inside the chamber and on the surface of the layer printed is very high. So there is local super elevation on the layers may also happen. Local super elevation or warping of the layers in common terminology. So these are the things, and then the corner accuracies are is always the biggest challenge in case of metal additive manufacturing. If you can see here, the different angles they have prepared. So this is results from the literature, and they have seen that all these corners are not sharp enough, and they can fit a circle to all these corners. That means these corners are radiused corners. Okay, so these corners are not a sharp corner. This is a radius corner, and it varies with angle to angle. So you can see for very small angles, you can fit a circle of 0.37. For another slightly bigger angle, you can fit 0.35. And when the angle grows, the circle fitting can be of 0.34 mm. So this is another challenge in case of metal additive printing. Now, to counter this, okay, we have planned the work on dimension in two different ways. First is we thought of doing it geometrically. Okay, geometrically means we do geometrical modeling of the surface, and let us start with first the flat surface or a planar surface, then slowly move to the inclined surface, see what are the different problems in dimensions in case of inclined surface. Then we move to slightly complicated features like a concave or a convex surface. And now at present, we are planning to move towards free-form surfaces. Okay, so we are trying to capture or cover all the aspects of the dimension inaccuracies, right from a planar surface to a free-form surface. So we have thought of this particular problem in two ways. First is geometrical modeling. Is there any way by geometry we can improve the dimensions of the component? So we print some dimensions, different dimension, we study the geometry of the final product after printing, and then we think then is there any way where our polishing method can play an important role to get the final dimension or to reduce the inaccuracy in the dimension? That is one way. Second way, which we have been doing, is on image processing side. Image processing means we take the sample, okay, after printing, and we extract the data from the image of the printed component, and we see is there any way we can play with the geometry of the particular sample or the feature, and can we suggest some ways to improve the dimensions in the next printing cycle. So these are the two major things which we are taking up in the dimension inaccuracy part. So as you can see, these are the three things which we have already printed, and we have done enough work on this, which is on an inclined surface. Okay, as far as I remember, this is a 60-degree inclined surface, and here we call this as a concave surface, and this is our convex surface. Okay, and now we are trying to find out the inaccuracies related to these surfaces, and these are the parameters for printing this material, these particular features. So these are the curved and inclined surface topography. Okay, so we have divided that into as built, as you can see here, and this is after polishing. Okay, so we are, as you can see here, this particular curves. Okay, if I take these particular features or the shape of these features, this cannot be done by a laser source. If you want to do polish, if you want to polish the surface, okay, using a laser beam, it is very difficult to encounter such a inclined plane. Okay, then if you have a hollow surface like this, okay, because the laser power is dependent on the energy incident on the surface. Okay, and when you move the laser beam on a curved surface, basically what laser is doing, laser is remelting a thin layer. Okay, it is remelting a thin layer on the surface. If it is remelting means, if you're doing some polishing here with a laser beam, if you're remelting means the molten material may fall, okay, or may not stay where it is supposed to stay. Okay, it may not fall because the cooling rates are very high, but still it may not stay at the place where it is supposed to be. Similarly, in case of a concave surface or a convex surface, if you are remelting a thin layer, that material have always a tendency to flow from its original position, and then you may end up incorporating or imparting more dimension inaccuracies to the surface. But that is not the case in case of EDM, because the amount of energy used in case of WEDM or WEDP polishing process is very low. Okay, the energy is very low, basically in microjoules. Okay, it is in microjoules, and you can see the surface for convex, inclined, and concave surface. So these are the surfaces before, and these are the surfaces after. And it is very easy to code this particular kind of surface on a wire EDM machine. So you just have to give the CAD drawing, you prepare our code for that, and then the wire will follow this particular, let's say this is your wire, and this will follow the whole curve like this. Okay, and again, I'm telling you, we are not cutting here, we are just brushing the wire on the top surface. Okay, so the wire is sensing the irregularity based on the distance between the job and the wire, and it is removing unnecessary peaks, and which includes like these balling defects as well, all these balling defects and unnecessary irregularities on the surface. So you could see in all the three cases, concave, convex, and inclined, we have got a very much smooth surface. Yeah, so this is the comparison of roughness. So here we have just shown the topography for the inclined surface, but if you see this particular bar chart, you can see in the convex, concave, and inclined surface, in all the cases, the roughness has been reduced drastically from the parent roughness of the surface. So now again, if you see here, the green one represents the bottom, mid. So let's say we have a section like this. So we have divided this section into top, this is bottom, and this section is mid. And we have analyzed the roughness at all three presses, because this job is made layer by layer. This job has been made layer by layer like this. Okay, now and the laser beam is somewhere here, which is scanning the surface. Correct. Now this particular bottom is built first, then on top of it we build the next layers. So we wanted to see what happens at the bottom, and then in the subsequent layers, when we print on top of the bottom layer, what happens at the middle section, okay, and what happens at the top again. Because as soon as the bottom layer is built, on top of it, the recoater blade will again pour the powder, and then the laser scanning will happen. Now, because of that laser scan, the bottom layer is still hot, and this is exposed to the gas outside, because here there is no more printing needed. So what happens to this surface if we produce, or if we kind of melt layers on top of it? So definitely these powder particles will get stick on this surface, because this is the bottom part, and the recoater blade has just covered the whole surface with fresh powder. So this spotter may get stick to this surface, and this is what the reason is. In case of all the bottom sides, you can see the roughness is higher in case of printing, because, and that is evident from the SEM images also. So if you see here, this is basically a convex part, okay, where you can see lot of spotter particles sticking to the bottom surface. Okay, so this is the surface like this. Okay, basically this is this surface, and this is the middle section where you can see irregularity. You can see bumpiness on the screen or waviness on the screen on the middle section. And here, this is the top surface. Again, you can see some particles sticking, but after polishing, we could get a finer surface like this. At the bottom, this is the middle section where the waviness has been removed, and this is the top section. Similarly, the similar observations have been made for the concave section, where at the bottom you can see a lot of deposition of spotter particles, because as I mentioned in the previous slide, the reason is that. And then the finished surfaces are like this. Okay. Now, up to this, we discussed from the point of view of studying the dimensions of each and every feature, be it inclined, curved, or whatever. Then we went into the geometrical modeling. Okay, so let's say this is my inclined surface, which is 60-degree angle, and this is the stair-stepping effect on the surface. And here is my wire. Now my job is to find out, and ideally, if I want to remove the steps on the surface, what I have to do, I have to cut this tip of the stair step in each pass of polishing. Okay, ultimately, I reach this particular line. Correct? So my job here is to find out what is the number of passes required to reach this particular final surface. Okay, as you can see, T is the layer thickness here, and H, this is H. H is the tip height from the final surface. Okay, and then we have done modeling, which I'm not representing here because this work is still under progress, and we soon will come up with a model which predicts the number of passes based on the angle of inclination and the tip height. Okay, this is for the inclined surface, but the problem becomes much more complicated when you talk about a convex or concave surface. So as you can see here, this is a convex surface. Okay, this particular thing is a convex surface. A part of it we have not modeled because it is symmetric, so we have taken a small part of it. And if you see here, the step on this surface is gradually reducing. The step is gradually reducing. Okay, and for such a profile, we have to write our own code. This can be done geometrically. Okay, we can do simple geometry, use trigonometry, and find number of passes and those things. But here we have to write your own code to define the gap between the wire and the sample along the edge of the profile or along the length of the profile. So length of the profile, you see the steps are reducing. And if the steps are reducing, the height of each step is also reducing. This is the height. This is the height. This is the height of each step, which is reducing along the length. And if it is reducing, the polishing depth has to vary also with the profile. So for this, the work has already been done. We have developed our own code, in-house code for this, and we have achieved very fine surface finish by removing all these steps from the surface. But certain finishing touches are needed for this work, which we are still doing. And the similar thing goes for a concave surface also. This is a concave surface where the steps are moving. So the model as well as the code for polishing such a material, a MATLAB code is ready. The only thing is the implementation on this. Few samples we have done it. We have verified our code, but we have to fine tune our code again to get the exact dimension as the CAD model which we want. So we are working on it as of now. So this this ends the geometrical modeling aspect of dimension inaccuracies. Now we move on to the image processing part. I'll just take some water. In the meantime, if someone has any doubt till this point, they can ask me. Okay, so coming back to image processing technique for improving the dimension of the printed components. So I'll explain you this with an example of an acute geometry, acute angle geometry. You see here I have an acute angle printed geometry. This is 3D printed using metal additive manufacturing, and this image is taken under 3D magnifier, okay, USB magnifier basically. And as you can see, for this particular image, there is a background, okay, and there is a feature here. So you have two things in this image, feature and background. So what we have to do is we have to bring these two things at the same level, so which is known as grayscale conversion. So we have done grayscale conversion. So you can see both the background and the feature are now grayish in color. So we have done a grayscale comparison so that when we are observing something on the scale, it should be on the same platform. Now, next step is to take the image of the background alone. Okay, so we have removed the sample, the acute angle feature, and we have taken the image of the background itself. Okay, so this is just the image of background. Now, if you see here, from this particular image, what we have done is we have subtracted the background image or the pixels of the background image, basically. So the literal meaning is we have removed the pixels of the background and we have just kept the feature here. So when you have removed the pixels from there, that means the background has become black. Okay, the background has gone black and you can only see the feature now. And now this feature has been changed to a binary feature. Binary feature means instead of a grayscale mode, it looks like a white version of the feature or a whitish version of the feature on the black background. So it is black and white combination where it is easy to identify the border of the feature. Okay, and then we can easily extract the pixels related to the border of this feature. So these pixels we can easily find out from the image. So this is the whole technique. Now, what we have done with this is we have extracted the pixels related to this image, the border of this feature. Okay, and we have plotted it here. You see, this is the feature, and this is, I think, 30-degree angle. This is a 30-degree acute angle. Okay, and as you can see here, the tip of this particular feature is again rounded. Okay, you can fit a circle here. Now, here comes our algorithm. What the algorithm will do. So the idea of this whole image processing method is to find out polishing depth with respect to the feature. Okay, so we extract the image features, get the pixel values, and from that pixel values will tell us what would be the optimum polishing depth to get the final feature size. So what we have done is the extracted pixels are plotted on XY plot, and we have taken few points, which is written as PQR and STU here. Okay, so we have taken an equidistant 3 points on the surface, and we have drawn a tangent to these points, which meet at one point somewhere here, let's say O. So which meets at point O, and ideally this particular job or this particular feature has to be up to this point. Okay, the metal should be available up to this point, but it is not there, correct? So, and in the small drawing here, you can see the same methodology which I am explaining. Okay, so this particular height from the top of the feature to the tip of the tangent intersecting gives you the polishing depth. Okay, now after taking that polishing depth, you can compute back and feed it into your YRDM polishing code, and you get a final feature like this. So this you can see here is very sharp feature. you can easily get a sharp feature like this. Fine. So this is how the image processing. So I just gave you the broader overview. There are a lot of things running in the background, which I'm not going into the details, but you have to develop your own code, and then you have to train your system also with number of images and those things which we have done. And then this polishing depth calculation also is done based on a code. Okay, so this code varies with different feature size or feature angles also. So we have done this for different angles, 30, 60, 30, 90, and 120, something like that. And then we have verified this, and it is working very well with all these features. And based on that, what we have proposed is, okay, before that, so here the whole process is serving us two things. We are improving the dimensions of the printed component, and at the same time, we are improving the finish of the, or the surface integrity of the component as well. So this serves us two purposes. Okay, rather than just improving the surface integrity and then separately working on grinding machine or mechanical polishing or some chemical polishing to work on the dimensions. But here in the same process, we are achieving the both. This is represented in this particular slide. So you see, this is the as printed sample, and this is the polished sample. And at the same time, we have reduced the dimensional inaccuracy. So that this is radial correction factor. You can see the radial correction factor for all the different angles, acute, obtuse, and orthogonal. So this is 90 degree. I think this is 120 degrees, and this is 30 degrees. So with one step, you can encounter two things, which is the surface integrity as well as dimension accuracy. And here you can see for different set of samples how the surface roughness has reduced for all the settings in the sense for different settings of laser printing parameters. Okay, so now how does this helps us? How does this helps us? Okay, so we have planned, or we have been working on a closed loop system now to implement these things into the next printing cycle, so that the next printing cycles will be much better compared to the existing printed samples. So you can see here, let's say this is my sample, okay, with a 30 degree angle, 120 degree angle, and a 90 degree angle here. So this is my first sample which I've printed using metal additive manufacturing. Then I've taken this sample for polishing. Okay, after polishing, the sample dimensions have reduced. So by the way, this sample is 15 mm by 15 mm by 15 mm. Okay. Now, after polishing, definitely we are removing a very, very small thin layer of material from the sample. Okay. So these dimensions may reduce, which has already been reduced. You can see here. Then it goes for polishing compensation. So we have seen that with this with our algorithm, we have found that what is the polishing compensation or polishing depth for acute angle. What is the polishing compensation for obtuse angle? What is this for a 90 degree angle? Okay. Now we know all these things based on our previous set of experiments. Now what we'll do is we will add these values to the CAD drawing, the existing CAD drawing of this particular sample, So which is 15 by 15 by 15. We'll add these compensation values, to the CAD drawing of this model, and then we can incorporate this into the next printing cycle. So in the next printing cycle, you print an oversized component, okay, based on the compensation depth or the polishing depth suggested by your code. And then you print the cycle, and then you do the wire electrical discharge polishing, and you get the final component of the exact dimensions as CAD drawing. So this is what we have been working on now, and we have already implemented a part of it. Some part is still going on, which may take another 1 month to finish. And then this closed loop dimensional and surface integrity monitoring system will work efficiently for producing any feature, okay, be it a curved, inclined, or a flat surface. Now, this particular code, whatever I have discussed, the image processing part has not been worked with, let's say, a free form surface. So if I want to apply this to a biomedical implant on today, that may not be possible because it has lot of curved features, curved in the sense of free form curved features, and which needs understanding and implementation of B-spline curves and all those planning and processing of different strategies for polishing such samples. But as of now, this is for angular components, simple convex and concave features, as well as for inclined surfaces. Planar is always there. So with this, I would like to conclude my talk now. And this is the summary of my talk, which is, as we discussed, that number of grievous injuries have been increasing over the years. And we have presented some data in the initial slide. So the demand is there. Okay. Although the demand is very unpleasant and unfortunate, but we have to save the lives of these people as well. So the demand is there, and which is continuously rising. Okay, so we have to tackle this. Second, again, the customized specific implants, the demand is increasing because every patient is different, every accident is different. Okay, so our metal additive manufacturing gives us the design freedom, high customization. So this is the best way. Again, I talked about the cost initially. The cost, as per the Indian government, is less than 1 lakh rupees. Okay, and I strongly believe that metal additive manufacturing can bring down this cost much lesser. Okay, so there's a huge potential there. Then post processing is inevitable. Whatever printing process you do, post processing you have to do. So you have to perform some or the other type of post processing, but we are proposing a post processing method which can take care of both the surface integrity as well as the dimension.
Hello, Afzaal. Am I audible?
Yes, sir, you're audible.
Dr. Afzaal, but are you able to listen Dr. Afzal's voice?
No, sir.
No,
Okay.
sir. No, sir.
Okay. Maybe there is an issue. I thought maybe there is a problem with maybe. Maybe you can chat with him then. Or inform to Afzaal through chat, possible. Afzaal.
Hello, did I lose the connection in between?
Yes, Afzaal.
When, Subbu?
When you start, like we maybe only one summary line we heard. After that, no.
Oh, okay. I'll quickly summarize again. Okay. So
Okay,
I don't know what is the problem here, but somehow
I thought there is a problem with my login. Okay,
no, I
problem.
realized it later when nobody responded.
Okay, fine. Please carry on. Yeah.
Yeah,
So
just 2 minutes more.
No problem. Like you have to share the screen again. I think I'll make
not allowed to.
No,
yeah.
make again. You came out from the co-host. Now I made you as a co-host. Please share the screen now.
Fine. Yeah. So this is the filing slide. I hope it is visible now.
Yes, visible.
Yeah. So the same thing. The injuries are increasing. The biomedical based patient specific implant is increasing. The demand is increasing every day. The design freedom is available with metal additive manufacturing only, so we can do it that way. As well as minimum scrap formation is there. We need very less raw material for metal additive manufacturing. So this is the best process at present, but unfortunately there are many challenges which needs to be overcome, which can be overcome sooner or later, but we have to work together to come up to that stage. Yeah, and then I talked about one important thing is the ceiling price of these implants, which government has already decided, which is less than 1 lakh for the complete knee replacement. Now, I have a strong belief that metal additive manufacturing can bring this price to approximately 50%. Okay, so that's the only way to move forward. And post-processing is inevitable in case of metal additive manufacturing. Whatever you produce, you have to do some or the other way of post-processing, like for laser polishing or chemical polishing or abrasive polishing. So we have proposed a method where we can take care of the dimensions as well as the surface integrity together in the same process. And the investigations are still going on. So we are exploring it from left, right, and center. So much more things should come out in due course. So this is all from my side. Thank you. These are my references. Thank you. So if you have anything to ask, please go ahead.
Yes, thank you, Dr. Afzaal. It's an excellent talk. You started from the need to how to take to your research. So I hope most of them might have learned how to convert your need to your research problem. Especially in additive manufacturing, polishing is a great challenge, and getting a dimensional accuracy also. So nicely address that issue. And then how did you choose the Viridium process and the available other methods? So you've done a great justification in that line also. Yeah. So with this small conclusion, I request the participants to pose a question to Afzaal if you have any. Dr. Afzaal, there are a few questions on the chat box. So meanwhile, I'll take it for you. Okay?
Please.
Yeah. One is just a minute. Yeah. So what is the issue with using magnesium-based composites for bioimplants with respect to steel or titanium through AM?
Okay, so one of the biggest challenge with magnesium-based implants is the strength. Okay, so the strength is not there compared to titanium, and the lightweight feature is always there, but strength-wise, if you compare with cobalt, chromium, titanium alloys or stainless steel alloys, the strength-wise it is much lesser. So it is still being used, but it is used at a place where the loading is different or loading is less. Let's say if you can use it for a tennis elbow, where the loading that is not that much and the size of the implant is very small. Again, most of the time, these magnesium implants are used to support the bones because they are light in weight and cheaper in cost. So these are few reasons. Basically, the strength-wise, they are not that strong. So let's say if you want to replace a hip or a knee, you cannot use a magnesium implant because most of the time you'll be running, walking, and your whole body weight has to be supported by the implant. So this is a major issue.
Okay. Yeah. Another question, it is related to this implants. Okay. In a real time, is there any implants made by additively manufactured thing? They started to use for the human body?
Yes, it is there. It is there, but at present it is very expensive. So I have shown you some slide where where is it? A hip implant was shown. Okay, so yeah, sorry.
Maybe,
yeah, this is the implant.
Yeah.
So this is the hip implant which is manufactured, but again, I don't exactly say that whether it has been used inside the body or not. But knee implants are there for using metal additive manufacturing.
So there is one question: is it possible to collect stem cells from teeth and use it as a toolkit for its entire life for organs and tissues replacement through additive manufacturing?
I did not get it. Again, please.
Okay. You can also see in the chat box. Yeah. So
sure.
Can you just open the chat box and then you can get an idea. So I think
is it possible to collect stem cells from teeth and use it as a toolkit for his entire life for organs and tissues?
It's like a bio-additive manufacturing kind of.
Yeah, so this particular thing comes in organobiologics. Okay, and definitely for bigger implants, this may not work. Okay, so the bigger implant means I discussed about femoral and tibial component. So how can you take this to grow something as big as a femoral component? Very difficult, right? But for a smaller places, like a part of a small part of the jaw is removed, then you can use such stem cells. But basically that is into biology, so we are not into those things that much. Okay, next question is, I hope that I answered that question.
Yes, absolutely. Yeah, please go. No problem. Fine.
Beauty Vijeta.
They're supposed to respond.
Sure.
Okay.
So I take up the next one.
Yeah, next question, please. Yeah.
What is the material used in hospital for stitching? Kindly give your suggestion. That is
like a staple pin. They're saying, right? Nowadays they're putting a staple pin. That is easiest. Okay,
so there are two ways to do it. Okay, first thing is the staple pin, and the other way is to thread. So let's say if the injury is grievous and it has to take, the surgery has to take place in multiple steps. So they use staple pins, and staple pins are again made of cobalt, chromium, and all these materials, biocompatible materials. So they do it once and then they staple it. Why do they staple it? Because as soon as a foreign body enters in your human body, a foreign component enters into the human body, the body will not accept it. It will straight away reject it. And what happens is you will see lot of water and then many liquids coming out from that particular problem. Let's say if you take an example of knee implant. So after the surgery, they keep a small pipe-like thing which comes out from your skin and which drains out the water for like 3-4 days. Why? Because the body has not accepted it, and it has identified that particular part as a foreign object, and it is resisting it somehow. And that water thing is getting accumulated between your knee, and then it has to come out. So for that reason, they do staple pins, because they cannot completely close it. They will only close it when that water in the implant completely drains off or dried out. Okay. So, and the other way of doing this is with our conventional threads, the surgical threads. So if the surgery has to be done in steps, they have to do it in different ways, the stitching part. I hope that is fine, Natarajan.
Yes.
Okay, so Mohammed Rafiq is asking, thank you, sir. My next query is how polishing allowances will affect on the cost of additive manufactured components. Definitely it will affect, because you see how much amount of material you're removing in each cycle. And we are very curious to, curious is not the right word, we are anxious to reduce the amount of material to be removed. Why? Because each layer of material to be removed in a polishing step has some cost associated with it. And our target is to go as minimum as possible to reduce, because in case of conventional fabrication, you have seen that it has multi-stage grinding process, multi-stage 5-axis machining process. So you lose a lot of material, and material is the first thing which is costly and very expensive in case of implant manufacturing. So our target is to reduce. So we are targeting the problem from two different angles, which is through machine learning and image processing, and geometrically and mathematical models as well. So our target is to reduce the number of passes of polishing. Okay, and for that, I think EDM is doing good as of now. Something is like happening in casting, providing allowance and then polishing. Yeah, it is similar to that. It is similar to that. So we have here, you have to take into account the shrinkage allowances, which we have not done yet. Okay, so we are working on it now. So the present work is on the shrinkage allowances. So we have printed many samples, right from ALSI 10mg to Inconel to titanium to stainless steel. So we have the properties with us. Now we are working on a mathematical model, how can we incorporate shrinkage into dimensions also. So whatever I just showed you is related to the outer dimensions, but inherent material property has to be incorporated, which we are working on it now. And once that is done, you may get a chance to listen to me some next time, so we can discuss that as well.
Thank you, sir. Thank you, sir.
Thank you, Rafiq.
And then again, Dr. Natarajan asked one question: material may be titanium or stainless steel, that related to stapler pin or that stretching wire.
Yeah. Yes, definitely it is. Basically, the staple pins are made of cobalt chromium, because that's the cobalt chromium or stainless steel, depends on whatever.
It is a bio-grade stainless steel.
Biocompatible.
Yeah.
Definitely. SS316L.
Yeah, correct. So,
yeah, any other question? You can unmute your audio and ask me.
Sir, actually, I do have a question.
So please go ahead.
In the finishing processes, that is a post-processing process, say, let it be laser, abrasive polishing, or mechanical, or even the wire electrical discharge polishing. So it is basically focusing on the external surfaces of the additive manufactured part. So if I have a complex internal geometry in a part, so is there any specific method that
Yes.
in post-processing that can improve the surface properties?
Very good question. So actually, I intentionally did not present those things here, because that is our next idea. How do we take care of defects and anomalies on each layer? Okay. So let me explain you quite broadly.
Dr. Afzaal, sorry to interrupt. Maybe if I understand the question in another way, he is asking that if features are internal features, for example, hole or something is there. If that you want to polish, how to polish? I hope that is a question from Anuj. Am I right, Anuj?
Yes, sir. That is the question, sir.
Anuj, so in that case, actually, the next step which we are doing is for finishing of internal cavities and hole using die sink EDM machine. Okay, so we'll generate intentional cavities like slots, circular slots, irregular slots, and we'll use EDM milling to polish those surfaces using the same logic which I just discussed in the last presentation.
Yeah, okay, sir. So it is there is no specific thing that is already available, and it is
okay.
To be,
so if you talk about that, mostly for internal features, they use slurry-based abrasives.
Okay, sir.
Yeah.
But there is a problem in that, sir, correct? Like
correct.
There you can't control the parameters. It's like a non-deterministic process. So whenever you want to stop the process, you can't stop immediately. That means the control is not there. Like in
definitely there is no control. And the other thing is when the abrasives may get stick to the internal surface, and that again forms irregularity on the surface. Okay, and then if you talk about dimensions, let's say you need a 40 or 80 micron internal hole, then the slurry size or the abrasive particle size is in that range, so you cannot use that. So you have to use some other process to do such internal features.
Okay, now there is a need now. Now there is a need. Then it's a good thing to people think how to make the process for this. Okay, because as Afzaal rightly said, that the slurry-based process, for example, abrasive flow finishing or magnetorheological finishing, that can be used. The problem is you can't control, and then there is a chance this abrasive may embed inside and then create a problem.
So there is one thing, Dr. Subbu, you cannot control the process parameters. The other important thing is you cannot control the dimensions of the component.
That also, yeah. Now you have to compromise the dimension. You have to also, yeah, correct. That is also true.
Okay. So is this the same case when using chemical etching method also, sir? Actually, in the literature review which I was doing, chemical etching method was used only once previously. So does the dimensional accuracy problem also comes with the chemical etching process?
Definitely. Chemicals are very hard to control because they do selective etching, correct? Some parts will get, if you see titanium aluminum alloy, titanium 6 aluminum 4V, so there are three components: titanium, aluminum, and vanadium, and they selectively etch all these components. Okay, that means in that case, handling the etching rate, maintaining a uniform etching rate or chemical wear on the surface is very difficult, and you end up getting some dimension inaccuracies all the time. And again, from the point of view of medical implants, chemicals are not allowed.
Okay, sir. So if it is electrochemical, it is the same case again.
Same case, same case.
Okay,
Same
okay,
case.
sir. Yeah.
You have to prepare masks otherwise, okay, to
Yes.
control the dimensions as well as the depth of polishing.
Okay, okay, sir. Yeah. Thank you, sir. Thank you very much.
Thank you.
So any other questions from the participants? Okay, if no more questions from the participants, yeah, then that case, like Dr. Afzaal, thanks for your talk and then sharing your time with us. I think we can wind up the second talk of today's session. Okay.
Sure. Thank you. Thank you all for listening patiently, and hope to see you soon in other talks. Bye-bye.
Thank you, sir. Thank you. Bye. Yeah. Now I request Saravanan, please share the feedback form. Yeah. So today, after lunch, 2:30, we'll have a talk. Maybe I will cover for 1 hour. It's related to rapid tooling. That is related to not level of the research thing. Okay. So there we can learn about that. What are the things there for the industrial point of view? Okay, how to make the use of this additive manufacturing for making a mold and patterns. And that we'll see today. But after that, we can have a demo session. Okay, so already I've just collected the information, like around 80% of participants are showing interest. So in that case, yeah, we can do it by today itself. When we now. So, okay, so is it the feedback form is working?